Okay. And kind of halfway through that lecture, I kind of like introduced this concept that we can start out with, start to build our own differential equations. I just went through that quick example in the exam where we start out with something like a statement that says, well, I think I know something about how the rate of change of some physical parameter will change with some other physical parameters. So for instance, in here, the rate of change of a plant's height increase is proportional to some natural logarithm in here. And that gives us some kind of rate of change of height is equal to the natural log of the difference in height between the tree and its maximum height, something like that. Okay, you can do the same with other states. So this is the cooling law. It gives us a differential equation. So what we want to do is, that puts us basically here in this kind of, in our kind of order of differentiating. We go from, say, like a displacement or an amount of stuff, okay, to a rate of change of stuff or a rate of change of position, so kind of a velocity or a rate of reaction or something like that, and then acceleration. And each time we're differentiating. Now, if we've got these equations where we've kind of built our own differential equation, we've started in the middle. Okay, so to get back to an equation that describes the amount of stuff or the position of stuff through time, okay, we need to kind of reverse differentiate. Okay, and this process of reverse differentiating is called integration. Okay, and it's kind of like the other part of calculus. So calculus really has two parts. One is differentiation, which is working out rates of change and stuff, and the other one is integration, which is working backwards from rates of change to get to absolute amounts of stuff. Okay, and we'll go through more examples of exactly what this is. Okay, so integral calculus. It is integral to calculus. So really simply, it's the opposite of differentiation. And mathematically, it's identical to the opposite of differentiation. So if you can differentiate something, okay, and you integrate it, you should always end up with what you started with. Okay, but in this case, we're starting out, rather than with an amount of stuff, we're starting out with a gradient of our function through time, and we want to get the initial function. Okay, and it's not just for mathematics' sake, it's actually quite useful for working out the area underneath curves, and we'll hopefully come to an example at the end why that's actually useful. Okay, so it might be, the really simple example is if you're in a car and you're recording the speed as you go along, okay, you could make a graph of speed through time, and if you integrated that function, okay, if you integrated that graph, you worked out the area underneath it, speed versus time, okay, that would be the distance you've travelled. Okay, so that's a really straightforward example, but we'll go on to one which is actually more useful in the end. Okay, so to start out with, we'll think about, if we start out with our really, really simple differential equation, okay, so we start out with the gradient dy by dx, okay, or y prime, is equal to 1/3. Okay, so we need to think of what equation we can differentiate, okay, to get that answer. Okay. Now, it turns out that there is an infinite number of equations that can get that that satisfy that gradient. Okay, so these are some of them. Okay, so this is y equals 1/3 x plus 0, y equals 1/3 x plus 3, or basically all of these graphs have a gradient of 1/3. Okay, so when we differentiate those, we could differentiate those. Let's differentiate the first one. If we were to differentiate, so our general form, you'll remember, of basically if y equals x to the n, dy dx is equal to n x to the n minus 1. Okay? Learn the fuck out of that. Okay? Now, if we're here, and we've got, basically, if we're saying that dy by dx equals 1/3, okay, how do we get up to there? Okay, so if we think about what y would be, okay, if we were to if we were to differentiate that function, okay, so this can be thought of x to the 1, okay, so we bring the 1 down to here, so that would be 1 times 1 divided by 3, so that's just a third, and 1 minus 1 is 0, so x to the power of 0 is 1, so that kind of disappears, so that differentiates to that, okay. The problem is that okay, if I put a constant after that, any number, could be 17,938, okay, if I was to differentiate that, okay, I mean that's the same, so if I was to differentiate a constant, that constant becomes, when you differentiate it, it disappears, right? Because you were basically saying, remember, you differentiate that part first and that part separately. So that goes to that, and then differentiate that part, okay, goes to 0. Yeah? You differentiate a constant, it's 0. So it turns out that when we integrate, when we go back, okay, we don't know what that constant is going to be. Okay, so when we integrate, we always have, so that's, I mean, that's what satisfies any of those curves. So we could have any number here after the 1/3 x, okay, could satisfy that gradient. Okay, so I mean, it could be anything. It could be 10,000. It could be a really, really small number. So when we integrate, okay, we have to have this constant of integration. Okay, so it's something that we don't know. Okay, so it doesn't matter what c is because we can always differentiate back the other way. Okay, and we'll come on to an example where we actually use this, and we'll find out that the c magically disappears. Okay, so when you're integrating, you do the opposite of differentiation. Okay, and then you add c, some constant, and it's really important that you remember to add that c. And c is called the constant of integration because it is a constant when you do integration. Okay, so these are the generic formula for integration. Okay, and we'll just do a very simple demonstration of this. Okay, so if we have a gradient of y equals x to the n, okay, the integral of that will be x to the n plus 1 divided by n plus 1 plus our constant of integration. Okay, and what I'm going to do is just if we think about if we were to differentiate this, okay, we should end up back with this. Okay, just to show that this works. So I'll make this go black. Okay, so this is kind of basically the generic formula for integration of any function where you've got x to the power of n. Okay, so just go through some examples of this. Okay, so if we had, say, y equals 2, and we wanted to integrate that function, okay, what would the answer be? And this would be a great time to do top hat. But so actually, I'll just flick through the next couple. Yeah. So if you could see if you could think about applying. Oh, I've rubbed it out like a tool. Okay, apply that formula to these. Okay. So if these are dy dx equals 2, what is y? makes it a little bit easier, because we're integrating with respect to x, these are 2 and m are just constants. You might think about rewriting the first one 2 times x to the power of 0. Yeah, because that's the same as 2, right? And m times x to the power of 0 might help. And then the other one is so we'll just work through the first one. So in this case we've got 2 times x to 0, okay? So the first thing we're going to do, I guess, if this is dy by dx, is equal to that. Okay? Keep the 2 in there. We're going to divide by n plus 1. Okay, so 0 plus 1 is 1. And then we're going to increase our power to n plus 1. So 0 plus 1 is 1. Okay? Plus c. And that's, so 2 divided by 1 is just 2. So we can just call that 2. X to the power of 1 is just x. Plus c. Okay? So that's the answer for that one. Okay? So have a go for the next one, for m. Integrate m. Go. You just sitting there really confident going, yeah, what's this going to do? Sometimes it's okay to sit there and be cocky if you actually done it. So if you finished, do number 4. Okay. So hopefully you should see that the m here. I mean that follows exactly the same guy as this one here. So that would just become m x plus c. Yeah. And you can see if you were to differentiate these, you would get back to our answer, right? And then this one would be 3 times 4. 3 divided by 5 x to the 5 plus c. Okay, so if you're a little unsure of those, then you should really kind of go through basically the last chapter in the blue book. But all we're doing is the opposite of differentiation. There's another. Okay, so we're going to go and talk a little bit now about the notation that we use for integration. So we introduced these lots of notation for differentiation. So we had dy dx and f prime of x, or kind of y prime, to show the gradient of something. Now, in our example here, we were integrating this gradient function to get this kind of like normal function here. But what if we didn't? Well, we're not integrating a gradient function. What if we're just integrating just any equation? Okay. So we have this terminology here with this kind of like weird elongated s. Okay. So if we were to, all this means is we're integrating this function, which is the function of a third, okay, with respect to x. So x is the variable that we're looking for in the equation to do the integration for. Okay, so it's the one that we basically whatever that variable is. So if we had an equation that was time t, and we were integrating with respect to time, this would be dt, and then anything in the equation, okay, that was t, we would basically, in our general formula, we would substitute in t for x. Okay. Okay, so the name of this long elongated s is called summer, because we're basically adding up the area underneath the curve or the line. Okay, and in this example, we're not saying whether there are any limits to the integration. So, in the case of our this has got a dy by dx of 1/3. Okay, we're working out the area underneath this graph. Okay, so this area underneath here, but we're not limiting it to anywhere. So this could go on forever. Okay, so it's impossible to work out the area under the graph because we're not providing any limits. Okay, and that's why we have this constant of integration, because we can't work out the area under the graph because we don't know the limits. Now, if we had some limits, if we wanted to know, if we at some point A and B along the x-axis, okay, if we wanted to know that area, okay, we can do that, okay, using what's called a definite integral. Okay, I think hopefully the next slide shows that. No, it doesn't. Damn. We'll come back to that. But just to point out that we've just gone through and shown the general case for integrating from going from a gradient to a kind of a regular function. So if these are the things we're integrating, okay, these are the integrals of that function. Okay, so you can kind of think of it that this is now, instead of this being the gradient function and this being our function, if we start out by assuming that the equation we're starting with is just the function we're interested in, and this is now a new equation that describes the integral of that function, which is mathematically identical to going from a gradient to the kind of the scalar function. Okay, so if we start out with 2x, we integrate that, and we get x squared. Okay, okay, because we would raise the power from 1 here to a 2. We divide by that power 2, so 2 divided by 2 is 1. That goes away. X squared. If we are integrating x, okay, we raise x to the power from 1 to 2, so that means it's x squared. But we then divide by that power, so divide by 2, so that gives us a half x squared. Okay, if we're integrating by a constant, that just becomes the constant times x. It doesn't necessarily become capitalised, that's just a typo. And this is our general formula here. If we have x raised to any power, okay, we just go 1 divided by the power plus 1 times x raised to the power plus 1. Okay, so we've just been through that. Okay, so those are the kind of the general cases, but there are kind of special cases that we need to think about as well. So there is this case of 1 over x. Okay, so you could write 1 over x as x to the minus 1, right? Okay, but if you did that, this equation here falls apart. Okay, because it would mean you're dividing by 0, and you can't divide by 0. It's not possible. So it turns out, and there is a very long and tedious mathematical proof of this, that actually when you integrate 1 over x, you get the natural log of x. Okay, I think that you can just accept that. It's not, I mean, if you really want to know why, the Khan Academy will tell you. Just like differentiating, e to the power of x becomes e to the power of x. When you do the reverse, when you integrate, it doesn't change either. And then you have the same kind of things with these trigonometry. Trigonometry? Are they trigonometry? Yeah, they are. Are they? These sine and cosine functions. Okay, so if you integrate sine, you get minus cosine. If you integrate cosine, you get a sine curve. Okay, so just bear in mind those. Okay, so we won't go through these examples because you've essentially just done some of those. But just like when we were differentiating, okay, and we had an equation that had multiple parts. So x squared plus x plus 3, something like that. Okay, multiple parts added together. When you're integrating, okay, and you had some function that is a function of x plus another function of x, okay, you very simply just integrate those separately and just add them together. Okay, same as if it's a minus. You just differentiate them separately and you subtract them. Okay. And if you had a constant times a function, and we've kind of done that one here, okay, 3 is a constant times a function of x, which is, in this case, x to the 4, okay, you just leave the constant out the front, okay, and you integrate the function of x. Okay, so in this case, we left 3 out the front, okay, we integrated our function of x, in this case, we took x to the power 4, okay, so that becomes divided by 5 and x to the power 5. Okay? You times that by 3 and you get answer, of course, plus the constant of integration. Okay, so same rules apply for integration and differentiation. And they get a red line around them. Okay, so let's just see if you guys can go through these examples here. So I want to integrate this function here. So x minus cos x with respect to x. So I want to see what that is. And this guy here, let's do this guy here. 3 divided by x. Ooh, that's hard. Plus 7 divided by x squared. So let's see if you can have a crack at those. Okay. Okay, so we're going to talk now about these constants of integration. So not constants, these definite integrals here. Okay. So what this means is that if we put a number above and below this squirrely s, this summer, that means we want to integrate that function between 2 points. Okay? And this is kind of, it's actually, what you actually do to do this is it's actually relatively straightforward. Okay, you just do the integration. You integrate it, and then you plug in the 2 numbers into the equations, and you minus the first number by the second number. So we'll just go through an example of that. Okay, so this is our equation, okay, that we want to integrate. So I'll draw that on the graph. So what we want to, we've got an equation that is y equals 5x. That's going to be something It's going to be something like that, okay? And we want to integrate that between 2 and 1. Okay? 2 and 1? Yeah. So that's 0, 1, 1, 2. Okay? So what we want to do is we want to know what that area is. Okay? So to do that, we integrate this function. Okay? So if we've got 2 between x equals 1, 5x dx, okay, that is going to be 5 divided by 2x squared. Yeah? So I've just raised the power by 1, so 1 becomes 2, and divided by that raised power, divided by 2. Okay, so, and that is, of course, plus c. Okay? Now, what we do is because we've got these start and end points, the area under that curve is, this equation is 5x squared over 2 plus c when x is 2 minus 5x squared over 2 plus c when x is 1. Okay? So you just do the integration, okay? And then you plug the beginning and the end points in and you just subtract them. Okay? So in this case, the area under this curve, well, first of all, you can see that this number minus this number, the c's are going to cancel out. Okay, this is going to be c minus plus c, so that's going to be, they're going to cancel out. Okay, so when you do a definite integral, okay, when you've got a beginning and end point, because although you don't know what c is, you know it's the same for any one curve. Okay, we can plug the numbers into this, so if we put 5 in here, so 5 times 1 squared, it's going to be 5, yeah? So it's going to be 5 over 2. And this we've got going to be 5 times 2 squared, so that's going to be 4 divided by 2. So that's going to be 5 times 4 is 20 something, maybe? No? Yeah, it's going to be 10. Okay? So 10 minus 5 halves. Okay? So 5 halves is 2.5. Yeah? So that's going to be 7.5. Now if we go to our graph now, okay, we can start to maybe think about whether that makes sense. Okay? So if this is y equals 5x, okay, at 1 here, that point there is going to be 1 along and 0 up. Yep? This is 2 along and 0 up. This one here is going to be 1 along and that is 5. Okay? So the area of that box there is 5 times 1. Okay? Now, this point here is going to be 2 times 5, so that's going to be 10, and it's going to be 1 across. Okay, and that is half of that, so that's going to be, the area of that is 2.5. Okay? So the total area is 7.5. Okay, so you can see for this really simple example of a straight line, okay, we could do this like fancy pants integration here, but just working out the area of a box and the area of a triangle, we get the same answer. Okay? Okay, but this approach will not work if we have a curvy line, if we have a more complex function. Okay? We could do that one, you could do that one. I recommend you go through those in your own time if you know. So if we have a curvy line, okay, so if we have some function like this, and we might want to know the area underneath that function. Okay. I don't want to do this example because we're out of time. Okay, I'm going to do this example. So this is kind of one of these word questions that kind of like might set you up for kind of the stuff you see in exams. Okay. So, assume we can describe photosynthesis uptake of carbon during some year, right? Doesn't matter what year, using the curve y equals x squared minus 9. So, where y is the uptake, and you can see that's amount of carbon per month. Okay, so that's a rate. Okay, okay. So the uptake of carbon from the atmosphere, okay, basically uptake of carbon into the atmosphere, is that equation there. Okay, and it tells you something about what x represents in terms of number of months from June. So we can draw a graph. Okay, and we can say 0 is June. Okay, and then July, August, September, October, November, December, and May, April, February, January, something like that. Okay, whatever the months are. Okay, and we could draw that curve, right? And that curve, well, so at 0, okay, 0 squared is 0, minus 9, so that's going to be a point down there. When x is 1, it's going to be 1 minus 9, so it's going to be kind of a little higher up here. Okay, and we're going to get some curve that looks like that. Okay, so you can see in the summer months we have a negative carbon uptake, carbon per month. Okay, so this is carbon going into the flux of carbon is going into the trees in the summer, and it's going out from the trees in the old winter. Okay, so we can identify the start and end points. So this is these points here, okay, where the net uptake is exactly 0. It says in the question to help you out. Okay, so this is when the basically respiration is overcoming photosynthesis until you get here, and then photosynthesis starts to be more than respiration, so our flux is down. So we could solve that equation for for y equals 0. Okay, so we could set 0 equals x squared minus 9. Yep. Okay, and that's actually quite easy to solve because you just say 9 equals x squared. So x is equal to 3 or minus 3. Okay, and those are these points. Well, I've actually done it. Minus 3 and minus 3. Okay. Okay, so that's fairly straightforward. Now, what I want to do now, the last part of the question, is quantify the carbon uptake by integrating the curve from the start to the end of the growing season. So what we want to do is we want to know that area. Okay? And if we think about what an area on this graph would be calculating, this is months. Okay, so on a graph like this, if we've got the y-axis is petagrams of carbon per month, and we've got months on the x-axis, so area would be this value times this value. So that would mean the months in the units cancel out, and we just get petagrams of carbon. Okay, so we can write our basically our definite integral. Okay, so between minus 3 and 3 for the function x squared minus 9. Okay, we just need to integrate that. Okay, so we can work out what that. I'll just get rid of the. How we've gone from kind of a word question like that. Okay, we've picked out the equation. Okay, and we've done things with that. So we've basically found points that are 0 to find out the start and end of the growth season. Okay, you You can do that to find also in differential equations to find out stationary points. And then we've integrated that equation, and that's told us something useful about the system. Okay? So it's told us kind of the amount of stuff underneath the curve. So hopefully that made sense.